Let us discuss GATE questions of the year 2022 for the subject Chemical Reaction Engineering. In the question number 26, it states that the reaction A gives rise to B is carried out isothermally on a porous catalyst. The intrinsic rate is kCa square, where K is the rate constant and Ca is the concentration of A. If the reaction is strongly pore diffusion controlled, what is the observed order of the reaction? That means, let us take this is a catalyst, porous catalyst, in which the reaction is happening on the surface and inside the pores. The inside the pores, the kind of average concentration is something around Ca, and the surface concentration of a molecule reacting is CaS. The external concentration of A is different than the internal concentration of A. So, because the concentration of A is lower inside the catalyst, so the rate of reaction or speed of a reaction is different from that of a surface, and you can able to find these concepts in the Elements of Chemical Reaction Engineering by Scott Fogler. If you follow this book, you can understand the lectures. Because the reaction is not happens at 100% efficiency, because the concentration of A inside the catalyst is lower than the outer surface or the bulk. So the efficiency will be lower. The efficiency is calculated in terms of the effectiveness factor. Okay, the effectiveness factor is termed as the rate of reaction of A, that means or overall average concentration of A in the catalyst, divided by surface rate. Because the surface rate will be higher than the observed rate, actual rate, the effectiveness factor will be less than 1. Okay, there are cases where the effectiveness factor can be greater than 1, don't worry, and at this effectiveness, that is efficiency or the effectiveness of a reaction, can be calculated by the ratio of rate of reaction of A divided by rate of reaction of A at the surface concentrations. Here it is given, there are some indications given in this. It is strongly pore diffusion controlled. That means, the A cannot able to diffuse faster into the the catalyst. Okay, that is why it is called pore diffusion controlled. The one which is slower, that is what it is termed as a controlled. The one which is slower is the diffusion of A into the catalyst, that is what's called pore diffusion controlled. If that is the case, what we have to supposed to calculate is observed order of the reaction. The actual order is A gives rise to B. This is the actual order of the A's. If it is an elementary reaction, the order of the reaction, you can see it's a 1 here. That is the actual rate of true. That means this is the actual reaction that is supposed to happen in the catalyst, right? But in reality, that particular order, that means the one which is supposed to follow this particular kinetics, in the catalyst, because of the speed or order of the reaction which is supposed to be go through at the speed of A gives rise to B as per the reaction, will not happen in the catalyst, because it is a pore diffusion controlled. In such cases, as it compared to the reaction A gives rise to B, which is the order of N3, and let us assume it's an nth order reaction that is given here, then in such cases, what is the actual order of the reaction happening inside the catalyst? Before we attempt this problem, you should know the few terms. What is the true rate or intrinsic rate, or the second one, it is called apparent or actual or observed rate. The true rate of reaction is when there is no pore diffusion, reaction happens at its own speed. Okay, that speed at which the reaction happens as per the stoichiometry, it is called, or as per the reaction, it's a true or intrinsic rate, the people call it as. And the reaction happens inside the porous catalyst is because of the diffusion of A. Then the observed reaction as compared to the true reaction is different. That observed reaction is called as the terms apparent or actual or observed. Wherever you see these kind of terms, then he is talking about what the actual rate of reaction is happening. The true rate is as per the reaction. The observed rate is what is happening, that is including the pore diffusion control aspects. So let us take the, if that is the case, what you are supposed to calculate when you compare it to the true reaction order, what is the actual reaction order is inside the catalyst. That is what you are supposed to calculate. Let us take, for example, the true or intrinsic rate as per the reaction is minus Ra equal to Kca square. Why it is given, okay, the order is 2. That means as per the reaction, the true rate of reaction is Kca square. Okay, let us see what happens. Observed, you have to suppose to calculate what is the observed rate, not the observed order, not the actual order. To do that, you are supposed to do some sorts of mathematics. Let us see that. Let us take the help of the effectiveness factor. Effectiveness factor is the ratio of the actual or apparent rate of reaction, that means what we have defined here, divided by surface reaction. That is, surface reaction and actual reactions are different, and therefore their actual rate of reaction is nothing but effectiveness factor into surface rate of reaction. So let us take the surface rate of reaction is K Ca power n. Let us start with the nth order. Later on we come back to the what happens when n equal to 2. Okay, so actual rate of reaction is nothing but effectiveness factor into Kn. N is the nth order rate constant into Cas power n. And for nth order reactions, okay, and how the nth order reactions, how this effectiveness factor is defined. When you wanted to suppose to calculate what is the effectiveness factor for the nth order reaction is nothing but 2 by n plus 1 power 1 by 2 into 3 by into phi n. Phi is the Thiele modulus. If you know the Thiele modulus, you can find it. You can able to find out the effectiveness factor. If you are able to find out the effectiveness factor using this expression, you can able to find out what is the actual rate of reaction happening here. So for the formula which connects the effectiveness factor and the Thiele modulus for the nth order is 2 by n plus 1 power half into 3 by Thiele modulus. What is Thiele modulus? Okay, the Thiele modulus is phi n square. In the in the majority of the textbooks, the phi n square is the Thiele modulus, which is nothing but Kn r square phi as power n minus 1 by dE. K is the nth order rate constant, r is the radius of the catalyst, Cas is the surface concentration, n is the order of the reaction, dE is the effective diffusion coefficient. That means you can, if you know these particular numbers, you can able to find out what is the Thiele modulus. Once you know the Thiele modulus, you know the effectiveness factor. Once you know the effectiveness factor, you can able to calculate rate of reaction. So let us substitute 2, 3 in 1. Okay, this is 1, this is 2, this is 3. You get an expression that minus Ra equal to 3 by r into square root of 2 into dE by n plus 1 into Kn power half into Cas power n plus 1 by 2. Now you take this as a constant because radius is constant, effective diffusivity constant, n is the actual order of the reaction which is constant, Kn is the rate constant. So the entire expression, let us take this as a Kn power dash, and Kn dash into Cas power n dash. What is n dash? N plus 1 by 2. If you compare the true rate of reaction with respect to the actual rate of reaction, if you compare these two, and where in place of n, what it is there here it is minus Ra. True rate is Kca power n, which is actual rate is Kn dash into Cas power n dash. If you see, compare these two equations, in place of n, now it has become n dash. How we can relate n dash to n? Simple. N dash is nothing but n plus 1 by 2. Okay, this is the overall equation we can able to, overall equation we can use. That means if you know the intrinsic rate, that means true rate of reaction is Kca square, 2 is the order of the reaction, that means you know the n, 2 plus 1 by 2. Okay, What is the actual order of the reaction? If you know the true order of the reaction, which is nothing but n plus 1 by 2, n equal to 2, if you plug in the numbers, the observed order of the reaction is nothing but 3 by 2. What is the actual order of the reaction? Which is 2, but the observed order of the reaction is nothing but 3 by 2. This is answer you are supposed to give for this kind of question. Thank you. Let us move to the next problem. Yeah, this is the question number 27. It is with respect to the enzymatic reactions. Okay, before we attempt to solve this problem, you should know a small basics about the reaction. In enzymatic reactions, the thing is the substrate, that is a feed molecule. In biochemical reactions, the feed molecule is termed as a substrate. E is the enzyme. That means enzyme will act on the substrate to form enzyme and substrate complex. This, after enzyme is attached to the feed molecule, which is substrate, the feed will be converted to the product and enzyme will be released back. So this is how the reaction happens. The enzyme will act on substrate to form enzyme substrate complex. This enzyme substrate complex will be transformed to form the product and the enzyme. So this is the base reaction. This is the Michael-Menten kinetics, kind of reactions. So what this happens is, sometimes along with the substrate and enzyme, there is a foreign molecule that inhibits the reaction. That foreign molecule is nothing but an inhibitor, which is represented by the symbol I. So, and what this foreign molecule do? This foreign molecule will attach to the enzyme, okay, to form E dot I. E dot means an enzyme inhibitor complex. That means once the inhibitor molecule is attached to the enzyme, this enzyme is not available for the reaction to happen. That means few of the enzyme molecules will form a complex with the inhibitor. Because of this particular reaction, speed of this particular reaction, which is formation of the product P, will be slowed down. Okay, that is what it is given. If this is the reaction, if there is inhibitor that is the present, then let us read the question now. In an enzymatic reaction, an inhibitor I competes with the substrate to bind the enzyme with the enzyme. That means this is some enzyme molecules reacted, combined with the substrate to form enzyme substrate complex, thereby reducing thereby reducing the rate of product. That means because of this inhibitor which is attached to this particular enzyme to form enzyme substrate complex, and it will slow down the formation of the product. The competitive inhibition follows the reaction mechanism. That means the inhibition, that means the enzyme attached to the inhibitor form enzyme inhibitor complex. If this particular reaction follows competitive inhibition, let us see the things. What is the competitive inhibition in the with next time, sooner. Let us follow. Okay, let S and I be the concentration of S and inhibitor respectively. Rs be the rate of consumption of substrate. That means the rate of consumption, because substrate is getting consumed, product is getting formed. Rs is representing how fast the substrate is getting consumed in the reaction. Assume the pseudo steady state. The correct plot of 1 by minus Rs versus 1 by S. That means if I plot the rate of consumption, 1 by rate of consumption on the y-axis, 1 by S, that is 1 by substrate concentration on the x-axis. If that is the case, among the plots which is given, which one are correct, which one are incorrect? If you observe the plots, and you can see, if you the option A will be the correct answer, which I am going to prove at the state. And here what is the case? There are two things is given. One is the curve with the presence of I, and another curve with absence of I. That means one is increasing the concentration of I, one is no inhibition. That means no inhibition means there is no inhibitor present in our reaction. If that is the case, how my profile will look like? If this reaction happens, that means presence of inhibitor concentration, how my profile is going to change. Here you can observe, here if you take these two lines, both lines originating at the same point, one having lower slope, one having higher slope. Here both have the same slopes but at different locations. The starting point is the different. Here the starting point is different and slopes are also different. Here you can see the slopes, the starting points are different and slopes are also different. One is at the lower and one is at the higher. So among these particular aspects, which one is correct? Okay, here in presence of inhibitor and in the absence of inhibitor, both starts at the same point, but because of the inhibitor, the slope of the inhibitor, slope of this particular line will be higher than compared to the no inhibition. Let us see a small comparisons between the two cases. And if you see the reactions, and the first one, that is in absence of inhibitor, this is the when substrate is combined with the enzyme to form substrate enzyme complex. The first reaction is a reversible reaction. The second one, few of the enzyme which is binded to the substrate will be converted to form some product and enzyme will be freed again. So the first one is the reversible reaction, the second one is the irreversible reaction. This is the mechanism that is assumed by Michael and Menten and kinetics. So this is how the pictorial representation, if I break down this equation into three different stages, the first one is substrate and enzyme to form enzyme substrate complex, and the second reaction, this and few of the enzyme substrate complex will form will again come back to the reverse reaction, substrate and enzyme, but few of the enzyme E dot S will give rise to product plus E. That means the enzyme substrate complex will reacted back to form the product P and the free enzyme. So if this is the case, the rate of reaction, this is also, and if you follow my my channel or earlier lectures of the GATE, I have explained how this equation has come up. Don't worry, you can able to refer to the elements of chemical reaction engineering by Scott Fogler. You can able to find out the answers. So for this Michael-Menten kinetics, minus Rs means rate of disappearance of substrate is nothing but the rate of formation of the product. That means if S is disappearing, P is forming. So minus Rs, that is disappearance of S, will be equal to the formation of the product, which is Vmax into S by Km plus S. This is the maximum rate. S is the substrate, Km is the Michael-Menten constant. Okay, if I transform this equation into Y equal to Mx plus C form, then minus 1 by Rs is equal to Km by Vmax into 1 by S plus 1 by Vmax. If you plot Y on this 1 minus 1 by on Y axis and 1 by S on the X axis, you get some line with slope Km by Vmax and intercept point is 1 by Vmax. And same reaction in presence of inhibitor, this is how it looks like. The reaction, the first reactions will be the same, with the substrate plus enzyme gives rise to enzyme substrate complex. This enzyme substrate complex gives rise to product plus enzyme. And additional reaction is happening, inhibitor and enzyme with the both will going to react to form E dot I complex. This is the additional, that is equation that is coming here. This additional equation in competitive inhibition, this is reversible reactions. Now what is this competitive inhibition? First of all, you can see wherever substrate enzyme want to attach to the substrate, at the same location the inhibitor wanted to attach to the enzyme. You can see the location, the enzyme is attaching to the substrate at the same location. For the same location, inhibitor also wanted to attach to the same location. That means for the same location, substrate and inhibitor trying to compete. That is why it's called competitive inhibition process. That means wherever the substrate wanted to attach to the enzyme, at the same location, inhibitor also wanted to attach. This comes under the competitive inhibition kinetics. So this is additional reaction. If you follow the mathematical formulations, finally minus Rs is equal to Vmax into S by S plus Km into 1 plus I by K. If you observe these two rate equations, there is additional term that is coming along with the Michael-Menten kinetics, which is 1 plus I by Ki. So let us transform this equation to y equal to mx plus c form. Therefore, minus 1 by rs is equal to km by v max into 1 plus I by ki, 1 by s plus 1 by v max. That means if I plot this equation on y-axis with minus 1 by rs, with x-axis 1 by s, there will be a line which is having the slope of km by v max plus 1 by ki. You can see here the intercept for the both cases which is the same. That means the origin of the line will be the common for the both the kinetics, which is the pure Michael-Menten kinetics, and the second one is competitive inhibition process. So among the options given, the correct answer is the lines which is originate at the same point, but the slope for the competitive inhibition will be higher than the no competitive process. Why? You can see this is the slope. What is the slope for this? Km by V max. What is the slope here? Km by V max into 1 plus I by Ki. Because this 1 plus I by Ki, this slope is always higher than the Michael-Menten kinetics. So the correct option is the slope of the graph. Okay, for the competition inhibition will be higher compared to the no inhibition process. And in reality, what is going to happen? Okay, if you conduct the reactions in a reactor, one which in presence, one there is no inhibitor is present, and second the inhibitor is present, you have maintained the same flow rates, the same concentrations of the feed, that is substrate in the reactor. The one which is having the inhibitor will proceed with the lower speed of reaction, because example, at the same concentration of the substrate, that means 1 by s, if you pick a point at 1 by s, draw a vertical line, it touches at the 2 points. For the no inhibition, it is touches at this point. With inhibition, it touches at this point. You can see minus 1 by rs. This is not rs, this is minus 1 by rs. The one which is at the lower will have the higher speed. The one which that is touches at the top will have the lower speed. There is a higher speed and lower speed. That means in case of no inhibition, the reaction proceeds much faster compared to the inhibition process. So the correct options will be the first one, rest are incorrect. Thank you. Let us move to the next problem. Yeah, it's a question number 62. It is said that consider the process in the figure. Okay, this is the CSTR. The reaction that is happening in the reactor is first reaction A plus B gives rise to P. The rate of decomposition of B is given, and second reaction is P plus B gives rise to S, that is rate of decomposition of B in the second reaction. The third one is S plus A gives rise to 2P, that means rate of decomposition of S. Among this, it is given that everything happens in a CSTR. Among the P is our main product, S is our it's a side reaction that is happening in the reactor. So if it is that is happening in the reactor, we have to find out, because this problem is the chemical reaction engineering cum optimization problem. You can see there are the products few there is a separator which is recycling the unreacted S, okay, unreacted S back to the CSTR. And the separator of job is unreacted A. It is again through the recycle of A, it is sending back to the reactor. And B is getting the unreacted B is removed. It is not sending back to the reactor, and the product P is getting removed from this particular separator. That means the separator does the job of recycling of A back to the reactor and recycling of S back to the reactor and removing the product B, unreacted B, and a product. That means B is only A is recycling, B, which is both A and B are which are feed for the reactor, B is they are removing, only A is they are recycling. And the rate of reactions are given, and the other information is given that K1, K2, K3 are the rate constants of the reaction, these three reactions. And the other information is given, the K2 equal to K3, that means rate constant of value of the rate constant K2 is equal to K3. And at steady state, the net generation of desired product, okay, S in the reactor is 0. That means S may be reactor, in the CSTR is 0. That means undesired product. That means the second reaction, which is the product S, the net formation of S is equal to 0. That is what is in the net generation rate of undesired product. That means S is not forming, not consuming. The net rate of generation is 0. Okay, that is, what else is given? The reactor volume is adjusted to maintain a constant single pass conversion of B. That means B is only passed a single time into the reactor. And for a fixed product rate, that is 90% conversion of B. That means they are targeting to the conversion of B which is getting into the reactor should be 90%. And the value of Q that minimizes some of the molar flow rates of A and S in the recycle stream. What is Q? The Q is nothing but ratio of XA by XB in the reactor. That means inside there will be 4 components will be present: A, B, S and P. So in that A, B, S, P in the reactor, the Q is the ratio is nothing but XA by XB. They are somehow trying to optimize, okay, by varying the Q. Q is nothing but the concentration of fraction of A by fraction of B which is there in the reactor. They are somehow managing Q. What happens? A Q that minimizes some of the flow rates of A and the recycle streams is. That means for a fixed product rate, the product is coming here. For a fixed product rate, they have somehow optimized the recycle A and recycle S. That is what is given. For a fixed product rate, that is product which is coming out, and 90%, that means they are targeting the 90%, and the value of Q that minimizes some of the molar flow rates of A and S in the recycle stream. That means we are targeting recycle A and recycle S. You have to somehow minimize for this fixed product, minimize the flow of A and S into the reactor using the value of Q. This is called the optimization problem. Let us tackle this in a efficient way. And you can see here I have drawn, it is a much better view, for a better view, fresh A and fresh B, recycle A and recycle S. The concentration, molar fractions of A, B, P, S are given here. There is a separator which, the F is the flow rate, total flow rate that is coming, exiting the reactor. In this F, A will be separated and recycling back, S will be recycling back, and the product is, product and unreacted, is removing from the system. Imagine, this is how, okay, Q, that means that somehow what is Q? Q is nothing but XA by XB. That means Q is XA by XB in the reactor. We have to find, what is a recycle stream? F consists of 4 components. One is A, B, P, S. Let us formulate F equal to total flow rate. In this total flow rate which is coming out of the reactor, among F, the component, the A, that means amount of A that is recycling back is F into XA. That means unreacted A which is recycling back, which is F into XA. B, F into XB, that means flow rate of B that is coming in the exit of the CSTR. F into XP, product flow rate, okay, this is coming which is getting removed from here. And recycle S, that means F into XS, that is in F into XS is recycling back to the reactor. Q is nothing but mole fraction of A by mole fraction of B. This is how you have to represent. Don't start with this, and you have to start with exit flow rates. And among this, what is the optimization problem? You have to optimize for a fixed product rate. You have to optimize the molar flow rate of A in the recycle and B in the recycle. What is the, for a fixed product that is coming out of the reactor is F into XP. For this fixed product rate, you have to somehow manage what is the recycle A, F into XA. What is recycle S? F into XS. Total flow rates of recycle A plus recycle S is FXA plus F into XS. For a fixed flow rate, you have to somehow minimize the recycle A and recycle S by using the Q. Okay, this is what, by managing Q, you somehow minimize this particular term. And XA, this will transforms to XA plus XS by XP. That means if you somehow using the value of Q, you can able to optimize this particular term, then that will be the solution. For maximum or minimum, you have to find out the derivative of this particular term should be equal to 0. d by dq of this particular term. But here xa is there, xs is there, xp is there. How you can able to take a derivative of d by dq of this particular term? It is very simple. Convert every variable xa, xs, xp in terms of q. So if every term is in terms of q, then you can able to get a derivative of this particular term, which you make equal to 0. Then you get a term at this condition, you get some value of q. That is what they are supposed to, you are supposed to calculate. What value of q you are in the reactor. So you can minimize the recycle A or recycle S for a fixed product rate, which is F into XP. So let us get this particular equation in terms of q. So it will be more practical. Let us take the first reaction. First reaction, A plus B is equal to K1 times P. P plus B is equal to K2 times S. S plus A equal to K3, 2P. Okay. Given information, K2 equal to K3 and Q is given as XA by XB. And the function value is XA plus XS by XP. And the another information is given, net rate of formation of S. S is an undesired product in our reaction, and in the question it is given net rate of formation of S equal to 0. Let us use this information, let us formulate and finally reach to the solution. Net rate of formation of S. Let us see the S. S is in how many reactions? Reaction number 2 and reaction number 3. In reaction number 2 it is forming, and reaction number 3 it is consuming. That means net rate of formation is nothing but K2 XP XB. You have to take as a positive because in the second reaction it is forming, so the first term will be positive. Net rate of the formation of S is K2 XP XB, and net decomposition of S is K3 SA XS. So in the second term we have to suppose to take as a negative because it's in the third reaction it is getting consumed. In this particular second reaction it is getting formed. So net rate of reaction is K2 XP XB minus K3 XS XA, which is equal to 0, which is given. From this we can get some information about the ratio of XA by XB is nothing but XP by XS, which is given XA by XP, which is nothing but Q. So this is given. So XA from this information is Q times XP, and XS, that means here XP by XQ. Okay, let us take this as a equation number 2 both. Let us substitute the values on in this particular function. The function value now it become Q into XB plus XP by Q by XP. Another information is provided, 90% of B is reacted. How much amount of flow rate? Okay, that is exiting the reactor, F into XB, which is nothing but 0.1 into B. Why it is 0.1 into B? Among only 90, because the 90% of the B is, if B is the inlet flow rate to the reactor, that means here, let us take this B is the inlet flow rate to the reactor, and by exiting after the reaction, 90% of B got converted. That means only 10% of B will come out of the particular reactor. Okay, if that is the case, FXB, that is amount of B that is coming out of the reactor, which is F into XB, is 0.1 into B. So there is a flow rate information. Let us talk about the C product, because XP is there, XB here. So somehow we convert XB and XP in terms of Q. So you can able to get entire function in terms of Q. So if you talk about the Q, if the let us take the 3 reactions. A plus B gives rise to P, P plus B gives rise to S, S plus A gives rise to 2P. Sum up, because in every reaction P is there. Let us try to get single equation among this particular 3 equations. If you summate all these 3 equations, you get 2A plus 2B plus S plus P is equal to S plus P plus 2P. Finally, A plus B equal to P. So by summing up all the reaction, there will be only single reaction, which is, will try to form the product P. That means if you follow this particular reaction, every 1 mole of B is getting reacted, 1 mole of P will be formed. So what is the flow rate of P that is exiting the reactor? If you see here, the flow rate of P that is exiting the reactor is F into XP. That means here, which is nothing but 0.9 into B. Why it is called? Because every 1 mole of B to form 1 mole of P. If 90% of the B is getting reacted, means 90% of the P is getting formed. So 0.9, that means flow rate, exit flow rate of P is F into XP, which is nothing but 90% of inlet flow rate of B. So from this information you get F into XP by F into XB by XP is nothing but 1 by 9. Okay, that means XB by XP equal to 1 by 9. So XB equal to XP by 9. So you can see now you are converting XB in terms of XP. So now every term is coming in terms of XP. Simply substitute in this particular equation F equal to Q into XP by 9 plus XP by Q by XP. If you XP, if you take out the common, cancels out. Finally the function value is nothing but Q by 9 plus 1 by Q. So for maximum or minimum you have to take a derivative of the function, make it equal to 0. So df by dq equal to 0, which is nothing but 1 by 9 plus 1 by q square equal to 0. So from this q square minus 9, q square minus 9 by q square equal to 0. So denominator cannot be equal to 0, only numerator is equal to 0. So q square minus 9 equal to 0, the q is nothing but square root of 9, which is 3. That means if you maintain the Q value in the reactor equal to 3, that means XA, the ratio of XA by XB in the reactor equal to 3. So minimum flow rate of A and minimum flow rate of S will be recycled back for a fixed product, which is called F into XP. For a fixed product, what is the minimum recycle S and recycle A? We can pump back into the reactor. Why we have to take the minimum? Because if minimum A is getting into the reactor, means maximum conversion is happening in the reactor, that is why minimum recycle is going back. So that is why it is called optimization problem. So here the value of Q that minimizes recycle A plus S for a fixed product is 3. So let us move to the next problem. Let me explain this particular question number 3 in as simple way as possible. There is a reactor, okay, with a fresh feed molar flow rate of, that means at this location 1 and location 2, it's a molar volumetric flow rate is 10 meter cube per hour. The concentration at the location 1 is Ca1, which is 2 kilomole per meter cube. It's a recycle reactor. So recycle ratio is given as flow rate, volumetric flow rate of and the recycle divided by exit volumetric flow rate. So R is nothing but VR by V2, and it's a PFR that is primarily present here. And the question is asked that if you try to increase the recycle ratio, that means if you try to increase the flow rate of the inner loop, this particular loop, what is going to happen? Okay, that is what let us take the example. If that is the case, if you infinitely increase the R, what will be conversion of A for a given initial concentration of A and volumetric flow rate of A? Now let us read the question. An elementary irreversible liquid phase reaction 2A gives rise to B is carried out under isothermal conditions in a 1 meter cube ideal plug flow reactor as shown in the figure. The volumetric flow rate is given and the concentration is given. In the first case, for a recycle ratio which is R equal to 0, the conversion of A at location 2 is 50%. That means if you remove this recycle loop, it's a only single PFR. In such cases, for a given concentration and volumetric flow rate, the conversion is 50%. Okay. Then in the second case, for if you try to increase the recycle ratio, that means for R tends to infinite, what is the conversion of A in this recycle reactor? That means case 1 it's only PFR, in case 2 it's a recycled PFR. So in the first information we try to get the because all the information is given except the rate constant. That means using the case 1, which is only PFR, get the value of k. In the case 2, when r tends to infinite, what happens in the particular conversion in the case 2. And if you go through the proper recycled reactor concepts, when you increase the flow rate on the recycle loop, that means if r tends to infinite, very high flow rates are going to happen, because inlet flow rate and exit flow rate will, because here location 1, location 2 flow rates will not change. The only thing is, if you keep a pump here at the recycle loop, the pump will force the liquid at a very high flow rates. That means as r tends to infinite, the flow is such a very very high in the reactor, so available space time for the reaction is drastically reduced. If the available space time is drastically reduced, the concentration the concentration will remain the same throughout the reactor for the reaction. And that means as you increase the recycle ratio, and the concentration over the entire PFR will be close to only single concentration. In general, what happens the case in the normal PFR, the concentration at the beginning will be higher than compared to the end. But here, because of the heavy flow rates, the concentration will be the same throughout the reactor, which is the case. It now in only one case, it will behave like a CSTR. That means as the recycle ratio tends to infinite, the concentration becomes evens out at every location in the reactor. That makes this is like a CSTR. In CSTR also, in the tank, if you remember, in CSTR, in the entire tank, the concentration will be the same. Okay. That is the same thing which is happening as the recycle ratio tends to infinite. That means for the case 2, you have to solve this like a CSTR to estimate the conversion here. As r tends to infinite, the flow rate into the reactor reaches high. At high flow rates, the molecules have a less time to react in the reactor, and the concentration of A will same inside the reactor at all locations. So the intention is to solve it like a CSTR. Let us see through case 1, we will get the information about the K. For the case 2, using the information of K which is calculated in the case 1, use it to find out conversion in the recycle reactor. Case 1, it's only PFR. Okay, it's only PFR, and initial volumetric flow rate concentration and the volume of the reactor, the conversion is 50%. Then volumetric flow rate is nothing but molar flow rate by concentration. So given information, 2A gives rise to B, that means it's a second order reaction. A minus RA equal to KCA square because it's a liquid reaction. CA equal to CA naught into 1 minus X. So with the K equal minus RA equal to K into CA naught square into 1 minus X whole square. If you take the design equation of the PFR, volume of the reactor is nothing but integral 0 to x Fa naught by minus RA into dx. If you substitute the rate of reaction of this particular term and integrate, you get the volume of the reactor is nothing but volumetric flow rate by rate constant into initial concentration into x by 1 minus x. We know x, which is 0.5, and we know volumetric flow rate, we know the concentration, we know the volume. So you can calculate the K from this equation. From this information, we can get the value of K is equal to 5 meter cube per kilomole hour. So in the second case, that means it's a recycled reactor is just behaving like a PFR. Let us use the design equation for the, it is behaving like a CSTR, because at infinite recycle ratio, the recycled reactor will become like a CSTR. So design equation for CSTR, V equal to Fa naught into x by minus RA. So Fa naught into x by K CA0 square into 1 minus x square. Using this information, and if you separate out, because now it will be a quadratic equation, because you are supposed to find out the conversion in the particular reactor. So if you formulate the things in a quadratic equation, the final equation is x square minus 3x plus 1 equal to 0. Because of a quadratic equation, the solution will be x equal to minus b plus or minus square root of b square minus 4ac by 2a. Among this, you are supposed to take the value which is more appropriate among the two solutions which we get. So therefore x means conversion, you get a 2. 2.618 and 0.38. Conversion cannot be go beyond 1. So this particular solution is wrong, and the one which is correct is 0.381. That means here it is a 50%. And the same reactor, same reaction, if you conduct in a recycled reactor where recycle ratio is very much higher, in such cases the conversion for a same flow rates, you get a 38.1. This is the answer. And thank you. Let us move to the next problem. Let me explain you the example question number 64. There are two reactors that were provided. The one reaction which happens is the gas phase reaction, and given in one reactor the pure A is going at a volumetric flow rate of 5 meter cube per hour at 400 Kelvin. The reactor volume, which is a PFR, the X is the conversion in this particular reactor is 80%. In the second case, and it's a CSTR, the temperature is different now, and it is at a 400 Kelvin. Now it is at 425 Kelvin, and volume of the reactor is 10 meter cube. Here in the PFR, pure A is going in. Here pure A is not going in. And in the 5 meter cube per hour flow rates, the concentration of A is 50%, and concentration of inerts which is going along with the A is also 50%. So let us move to the problem now. An elementary irreversible gas phase reaction is carried out at a fixed temperature and pressure in two separate ideal reactors. One is plug flow reactor of volume 10 meter cube, and second is CSTR of volume 10 meter cube. If pure A is fed at a volumetric flow rate of 5 meter cube hour to the reactor operating at 400 Kelvin, the conversion here they are getting is 80%. If a mixture of 50% of A and 50% of inert is fed at a flow rate of 5 meter cube per hour to the CSTR operating at 425 Kelvin with reactor volume of 10 meter cube, meter cube. So the universal gas constant R equal to 8.314 is given. Assuming Arrhenius law is valid, estimate the activation energy of this particular reaction. That means two separate things are given. Both they are getting 80% conversions. One is running at a 400 Kelvin with the pure A in a PFR, and one is running at a 50% of pure A at 425 Kelvin. What we are supposed to find out it, the reaction is same in both the cases. We are supposed to find out what is the activation energy of this particular reaction. So the K value, that means from this particular case you can get the K at 400 Kelvin. From this particular case you get a K, that means rate constant K at a 425 Kelvin. Let us take the K1 is K400 and K2 is K at 425. If you know both the information, using this equation you can able to find out the activation energy E. Activation energy is nothing but minus R into ln K2 by K1 by 1 by T2 minus 1 by T1. So let us get the values of K2 and K1. That is what this we are supposed to calculate. And here, if this you take a particular reaction, imagine this is a gas phase reaction. Things will be a bit extra step is required. So A gives rise to B plus C. The reaction is minus R equal to KCA. In gas phase reactions, the concentration of A is CA0 into 1 minus X by 1 plus epsilon into X. So this epsilon term you are supposed to integrate in the equation. How to supposed to calculate epsilon? Epsilon is nothing but Ya naught into delta. What is Ya naught? What is the mole fraction of A in the feed? What is delta? Delta is nothing but stoichiometry coefficient of the products minus the stoichiometry coefficient of the reactants. What is the sum of the stoichiometry coefficient of the products? 1 plus 1, which is 2. What is the stoichiometry coefficient of the reactant, which is 1? That means 2 minus 1 is 1. And Ya naught, what is in the reactor, pure A is going into the reactor. So the mole fraction of A in the feed is Ya0 equal to 1. So you got both the informations. So you can calculate epsilon. You can calculate this is delta. Let me correct it. This is delta. Ya naught into delta. This is delta. If you know the Ya naught into delta, you can calculate the epsilon. Design equation for the PFR. 0 to volume is equal to integral 0 to x Fa naught by minus Ra into dx. Substitute the value of Ra, which is here. and epsilon which is equal to 1, that means y naught equal to 1 and delta equal to 1, that is both epsilon equal to 1. So if you integrate, finally you are going to get v equal to v naught by k into minus 2 ln 1 minus x minus x. Okay, from this you can, what is x, what is k, that means rate constant at 400 Kelvin for the PFR is nothing but V0, that means volumetric flow rate of flow rate by volume into minus 2 into ln 1 minus x minus x. X is given, it is 80%. If you substitute the values, you get k at 400 Kelvin is 1.209 per hour. Okay, similarly we can calculate the next k using the information of the CSTR. The same, it's a 50% A and 50% inerts. The design equation is V is equal to Fa naught and x by minus Ra. Here the things changes because it is not a pure A. Now A is with the inert. So the epsilon will change now. Epsilon is nothing but Ya naught into delta. What is Ya naught? That is initial mole fraction of A in the feed, which is 50%, which is 0.5. Delta, which is the same, 2 minus 1, which is 1. So the epsilon value is Ya naught into delta, which is 0.5. Simply using this design equation, you can calculate k is nothing but volumetric flow rate by volume into x into 1 plus epsilon x by 1 minus x. Substitute the values because volume is given, volumetric flow rate is given, conversion is 80%. By plugging all the values, you get the rate constant at 425 Kelvin is 2.8 per hour. Okay, if k1 is given and k2 we have got, so using this activation energy is nothing but minus r ln k2 by k1 by 1 by t2 minus 1 by t1. If you plug in all the values, you get the value of 47496.57 joule per mole. Because the value of r you are taken joule per mole Kelvin, the activation energy you are going to get 44 joule per mole Kelvin. But in the question it is asked to mention the number in terms of kilojoule per mole Kelvin. So if you convert this to the kilojoule, 47.49 kilojoule per mole is the activation energy of this particular reaction. So let us move to the next question. It's a question number 65. It's a straightforward question that an elementary irreversible liquid phase reaction 2P gives rise to Q, where the rate constant value is given 2 liter per mole per minute, takes place in an isothermal non-ideal reactor. So the E curve in a tracer experiment is shown. That means the E curve. The pure P is fed to the reactor. That means if that is the case, if there is a reactor which is non-ideal and the P, the pure P is fed to that particular reactor, and using the non-ideal model, which is segregated model, we have to find out what is the conversion of P in that particular non-ideal reactor given the RTD curve of the reaction. RTD curve of the reactor. So let us solve and assume this is our non-ideal reactor in which the reaction is going to happen. K is given. The segregated model, that means the conversion from this non-ideal reactor can be calculated. Okay, x bar equal to integral 0 to infinite E of t into x of t. If you know the E of t and x of t of this particular reactor, then you can able to find out what is the conversion in the particular reactor. What is E of t? The residence time distribution data which is provided, and x of t is nothing but the conversion from the batch reactor. That means in a non-ideal reactor, in the segregated model, it is assumed that inside the reaction happens in a batches. Okay, that is why in this particular x of t, what is the conversion of this particular batch reactors? So finally, if you can able to integrate, you can able to find out the conversion from the reactor. So let us get the expression for E of t and x of t separately and integrate. You get the final value. What is the conversion from the reactor? X of t is the batch reactor conversion and E of t is the residence time distribution. Let us get the function for E of t. E of t it is given that in case of, let us divide this particular E of t curve into two portions. One is upper half is a right angle triangle and the bottom is a rectangle. Let us call the rectangle area is A1 and the right angle triangle area is A2. So in RTD curve, the area under the curve should be equal to 1. That means integral 0 to infinite E of t dt. That means the area under the curve E of t versus t should be equal to 1, which is equal to the 1 which is equal to area 1 plus area 2. What is the area 1? Base into height. Base is 0.5 time and height is 1 which is given. What is A2? That means area of the right angle triangle is half base into height. Base is also 0.5. Height, let us assume h is the height of the right angle triangle. So half into base into height. A1 plus A2 equal to 1. Using this information, you can get what is the h. H is nothing but 2. That means we got the information of h. So using this information, let us take one point is at A point and second point is a B point of the curve. In this particular curve, we know the 2 points. Using the 2 points information, construct a line which is linear connecting point A and point B. Let us take the value of the point A is 1, 0 and point B which is here which is 3, 0.5. That is 1, this is h is 2, the total is 3. Okay, I know y1 x1 and y2 x2. I can construct the graph y equal to mx plus c. What is m? y2 minus y1 by x2 minus x1. C which is already given, the intercept is 1. What is y? Which is nothing but e of t. What is x? Which is nothing but time. So if once I calculate the slope from slope of this equation, I get the equation e of t, that is y equal to mx plus c, that is 4t plus 1. So I got the information about the e of t which I can able to plug in this particular equation. Let us get the information about the x of t. X of t means the conversion from the batch reactor. So the design equation for the batch reactor is time t equal to Na naught into integral 0 to x dx by minus Ra into V. Get this volume out of the integral because, and it is a constant volume batch reactor, Na naught by V which is nothing but Ca naught into dx by minus Ra. Minus Ra I already know, I mean K, Ca equal to Ca naught into 1 minus x. So simply you substitute the value of rate in this particular equation and you can able to find out that time t equal to 1 by k Ca naught into integral 1 minus x power minus 2 into dx. You can able to do this integration. You get the time information t equal to 1 by k Ca 0 into x by 1 minus x. If you take a conversion on one side, time information on the other side, finally x is nothing but k Ca naught into t by 1 plus k Ca naught into t. This is for the second order reaction. So I know the information about the x. Simply the conversion from the reactor is nothing but integral 0 to infinite e of t into x of t. E of t information is 4t plus 1 into 4t by 1 plus 4t, which x of t information. Simply you integrate, you get the conversion from the reactor for the time 0 to 0.5 is 0.5, which is 50% conversion. That means from this reactor you can expect the 50% conversion using segregated flow model. Okay.